Hey everybody, Dr. Duncan here, and we're going to be talking today about climate and biodiversity. This is part of our continuing saga to understand how biodiversity is relevant to our lives and why Alabama has so much biodiversity compared to other states. And today we're going to learn about one of the major factors influencing biodiversity on the planet, which is, of course, climate. Now, before we get started, let me remind you that I've been giving you some tips on how to use these video lectures. I'm not going to go through all of them this time, but you may want to go back to the previous class, class 4, and review the tips that I gave you on how to watch video lectures and how to integrate them with your study guide. And of course, reach out to me with any questions that you have. I'm always happy to help you out, no matter where you are in the process of getting ready for the next exam and learning the information. Okay, well, let's get started. All right, so Alabama is, of course, ranked number 5 in the U.S. amongst states for its total biodiversity, and number 1 among states in the eastern U.S., which is about half those eastern states. There are several reasons for why Alabama has so many species. Despite what this slide says, I'm going to list them all out here for you now so that you can have them in your notes. The very first reason is that we have a very warm and wet climate. That's what we'll be talking about in this class, this lecture. The second reason has to do with the state's very diverse geology. A third reason has to do with the rich evolutionary past that has led to why we have all these species to begin with. And the fourth reason is that just has to do with the way the lines were drawn on the map. So Alabama is a tall state. It goes from the Gulf Coast, which is almost in the subtropics, all the way up to the Tennessee Valley, which is in the middle of the continent and gets really cold during the winter. That diversity from north to south, plus it's having access to the coast and a little bit of the mountains, all that adds up to a great diversity of ecosystems. And a lot of that has to just do with the politics of how European nations were dividing up the North American continent that they took away from the Native Americans, and then how the states of Mississippi and Alabama were divided when the territory was split up into the two new states. Okay, so let's focus on why we have such a warm, wet climate in Alabama. It's not quite as simple as one might think. Climate, of course, is a major factor in influencing where biodiversity is on the planet. Some of the reasons for this have to do with the fact that climate governs the availability of water via rainfall and other forms of precipitation like snow and ice. And also the climate regulates like how much heat a region has, and also climate is tied into the amount of sunlight that a region of the planet gets. So if you were paying attention there, you might have noticed that I listed off several of the factors that are in that formula that shapes ecosystems: heat, water, and sunlight. The one factor climate does not affect as much is the soil nutrients. That has more to do with geology, and we'll take up that topic in another class. Okay, so let's cover 4 physical processes that are the foundation for understanding the weather on the planet. With these 4 physical processes, several of which I think you already intuitively know, if you don't already sort of have a solid handle on this, I think you intuitively know this stuff for several of them. And with these 4 physical processes, you can understand the climate anywhere on the planet, and I'll show you how. Okay. So to begin with, let's see you quiz yourself on what you know so far. All right. So let's say you have a car, or you borrowed a car, and it's parked in a parking lot in the summer, and it gets superheated to 135 degrees Fahrenheit during a summer day. Dangerously hot, actually. This is why you don't want to leave people or organisms in a hot car with the windows up. And anyway, that's obviously quite hotter than the air outside. In the early evening, when you go to get in your car, you open the door and it's much cooler outside. It might be 85 degrees on the inside. It's still like 110 or something like that. What happens to that hot air when you open the door? Does it sink to the parking lot surface? Does it rise upward? Does it move sideways across the parking lot? Or maybe it just sits in the car? What do you think happens? Spend a moment, think it through, and then come back. Okay, so you probably already knew, but don't feel bad if you didn't, that that warm air would rise upward. It's not the sort of thing that we think about all the time, but that is it is certainly true that warm air rises compared to cooler air around it. And this cartoon on the left helps illustrate this very first principle that I want you to learn about physical conditions in our atmosphere and what governs them. The first one is that warm air rises and cool air tends to sink. Okay, I have a picture here of hot air balloons because, of course, the reason they work is that they superheat some air that's trapped inside the balloon, and because that air is warmer than the surrounding air, it winds up creating the physics of it winds up creating the rising air. That warm air inside the balloon wants to rise. It's being forced up into the atmosphere like a bubble rising to the surface. Okay, because that air, that warm air, is under less pressure, it's why it rises up out of the more higher pressure air around it. Just like a bubble is under much lower. It's under lower pressure than the surrounding high pressure of the water around it. Okay, so that's how that works. So that's why warm air rises. Okay, so a second physical property is that because of changes in air pressure, warm air tends to cool as it rises. Now, this is something that has to do with atmospheric pressure, and because of that, that's something that's not quite as intuitive to us. So let me try to explain. At the Earth's surface, so the atmosphere, I want you to imagine our atmosphere as layers of air stacked on top of us, and realize that that air is composed of molecules. And even though they're small, those molecules are under the influence of gravity. Gravity likes to pull those molecules down towards the Earth's surface. And for that reason, the atmosphere close to the Earth's surface is much thicker, has a higher density of those molecules than the atmosphere high above us. Okay, and you don't have to go very high off the Earth's surface in order to experience this. In fact, we can travel up mountains like the one you see in this picture, and climbing up just several thousand feet, you get to a point where the atmosphere is thinner. There's less thinner, meaning there's fewer air molecules in there. Now, of course, air is composed of many different types of molecules: oxygen, nitrogen, carbon dioxide, et cetera, right? We'll just call them air molecules for short. And so at these higher elevations, you can actually feel that because you have a harder time absorbing. If you're used to low elevations, your body's not used to the high elevations, and so you have a harder time absorbing oxygen from the atmosphere, and it takes a couple of days to acclimate. But then once you acclimate, you can go back to sort of feeling energetic just like you would down at the lower elevations. Okay, well, all of this has to do with differences in atmospheric pressure at different elevations. Okay, warm air, as it rises, it goes up to parts of the atmosphere up above where that warm air can expand, and as it expands, it cools. Okay, so I want you to think of like if we heated up a chunk of hot air, say above a candle or a fire or something like that. When we heat up that air, we are adding energy to the air molecules. And when you add energy to molecules, whether it's solid, a liquid, or a gas, those molecules start to, they're energized, they start to bounce around and move around much more quickly. And I want you to imagine when you heat up some air or some water, it's like you're taking a bunch of preschoolers and feeding them sugar. They want to start running around. They want elbow room. They want running space. Okay, that's how they try to reach back to equilibrium, is like sort of throwing off that energy through motion. And if you imagine heating up a chunk of air close to the Earth's surface, say over a fire, that air, all those molecules in that warmed air, they wants to move around. But when you go beyond that bubble of hot air, it hits colder air that's nearby. Well, colder air tends to have a bunch of molecules that are slow and lazy, and they're sort of thick and kind of packed together. They don't want to expand. They don't want anything to do with this monkey business. So what happens is that the warm air, all those molecules that want a lot of extra room to move around, it goes in the only direction it can go where it can have room for those molecules to bounce around and expand, and that's upwards. And so warm air starts rising upward like a bubble into the upper atmosphere. And as that warm air rises up into the upper atmosphere, because the atmosphere is thinner up there, there's not as many molecules. Those little toddler molecules that are hyped up on sugar, actually heat in our case, can actually start expanding. They can start zipping around, bouncing around over much greater distances before hitting into another molecule than they were down below where the atmosphere is very thick. And because they're able to expand and able to do that, the temperature of the air drops, because temperature is a measurement of molecular motion. When you measure something like water and you measure the temperature of that water, it's because the molecules are energized and they're bouncing into one another. That's what heat is measured as. That's what temperature is a measure of. And so as that warm air rises to the upper atmosphere, it can expand. It's got plenty of room for the molecules to bounce around, and therefore the volume of that gas expands and it winds up cooling. And that's why warm air rises and cools. Now, hit the pause button here for a second. Not literally, but hit the pause button here for a second. I gave you a lot of explanation about like why this happens, but you don't have to know that. That's more appropriate for a physics class. I think it's helpful to understand why it happens rather than just taking my word for it. All you need to know is that, like all that I might quiz you on, a quiz or an exam, all you need to know is what's written on this slide, that because of changes in air pressure, warm air cools as it rises, and the opposite is also true. Cool air tends to warm as it sinks. Okay, the reason cool air warms as it sinks, if you take cool air and you bring it down close to the Earth's surface, all the surrounding air starts squeezing it together, and when you squeeze it together down here close to the surface, where the atmosphere is very thick with molecules, those molecules wind up bouncing into each other a lot, which raises the temperature. Okay, so these are just like in the previous slide where warm air rises, cool air sinks. Similarly, warm air cools as it rises and cool air warms as it sinks. Okay? All right. Again, all you have to know is what is on this slide. One way to remember this is that picture right there of the mountain, right? You have in places where there's a high elevational gradient, you're going to have your cooler temperatures up at higher elevations, not at the lower elevations, because things are cooler at higher elevations. Okay. So we're going through 4 different physical properties that help explain weather patterns on the climate. Here's our third property. I think this is one that'll be much more intuitive for you than the second one. And this third one is that warm air tends to hold more moisture as water vapor, which of course is gaseous water, than does cool air. Okay, so think about which season is more humid, summer or winter. Down here in the southeast, our summers are much more humid. It is wet all the time, even when it's not raining. The humidity in the atmosphere is very high. And that's because warm air holds a lot more moisture than cold air. Okay. One way you can see this in action is that on a cold day, when you go outside and exhale, you get that cloud of steam out in front of your face. Well, what's happening here is this. When you inhale, you're taking air into your lungs, and from your lung linings, there's water that evaporates. Our lungs are moist on the inside. And as that water, it evaporates from your lung linings into that air that you inhaled. So then when you exhale, you're exhaling your carbon dioxide, which is the waste product, plus whatever air is inert and doesn't get, used by your body or anything like that. So you're exhaling the carbon dioxide and this inert air, and you're also exhaling all that water vapor that evaporated off your lungs. Well, that air that you're exhaling is, of course, very warm. Your breath should be warm. If your breath is not warm, then you got some issues, okay? Your breath should be warm. And as it comes out, that warm air with a lot of water vapor in it is going to hit that cold air. And because cold air can't keep water as water vapor very well, what happens is that the water molecules condense. They wind up condensing into little droplets, and that's what's causing the fog or the steam here. And the reason this is happening is that the water molecules, when they're evaporated as a gas, they're warm, they're bouncing into one another and then bouncing off of one another, sort of like, you can imagine like sort of a bunch of balls, like each ball representing a water molecule, sort of zipping around through space, and they collide every once in a while and they bounce off each other and so forth. As long as that air is warm, there's enough energy to keep the motion of those molecules active all the time, like so that they just bounce and ricochet off each other. However, when that air starts to cool down, what happens is the molecules slow down. And when water molecules slow down enough, when they bounce into each other, instead of bouncing off and away, when they come together, they wind up sticking. And so you wind up getting, because of the charge on water molecules, they wind up sticking together. And the more of them that stick together, the bigger the droplet. So what essentially I'm saying here is that as you exhale this air in your lungs with all this water vapor that you can't see, because it's just like the humidity that's around you right now, you can't see it. It hits the super cold air on the outside. The water molecules glom together, they stick together instead of bouncing off one another. That forms the droplets. And that's an illustration of why, or the fact that warm air can hold a lot more water vapor than cold air. Okay, so this winds up being important for understanding weather and climate, because as warm air rises, it cools, and this is what we've learned with our previous two physical properties. Warm air rises, and when it does, it cools, and because it cools, it's unable to hold water as a gas. And that's why we have clouds up in the sky and not down here where we're living, except for under weird weather conditions. And that's when you get fogs. Okay. All right. So we got these three physical properties so far. We got one more to go through, and it's not that hard. And then we'll start pulling all this together. Okay. The fourth physical property I want you to learn is that land and air change temperature a lot faster than water. Water is stubborn. When it's warm, it likes to stay warm. When it's cold, it likes to stay cold. That's a good thing for us in many ways. I got my my mug of coffee here, and it'll stay warm for the next few minutes. I might even finish this lecture out while the coffee's still warm. Yum. Okay. An example of this you might be familiar with would be if you've ever been to the beach or to a lake during the spring and gone for a swim. During the spring, things might feel very warm outside. The air temperature might be in the upper 80s or something like that. And you think, oh, it's going to feel great to jump in the water. And then you jump in the water and you're like, oh, it is so cold. Okay. The reason is that water is lazy. It does not want to warm up. It takes a long time to warm up. And the converse is true in the fall. If you go down to the Gulf of Mexico, for example, or a lake here in Alabama, if you go down to the Gulf in, say, at fall break, like in October or something like that, it can be kind of chilly outside, but you jump in the Gulf and it's like pleasantly warm. And that's because in that case, the Gulf doesn't want to let go of its heat. And so that's why hurricane season continues well into the fall, even though temperatures on the continent have cooled down a bit. It's because the Gulf is retaining that heat. All that water is retaining that heat. Okay, so we got our 4 principles there. Let's do a quick review, okay? Number 1, warm air rises, cool air sinks. Number 2, because of changes in air pressure, warm air cools as it rises and cool air warms as it sinks. Number 3, warm air holds more moisture as water vapor than cool air. And then finally, land and air change temperature much faster than water, okay? Now, what we're going to do next is pull these together to explain global climate patterns. All right, so we're going to, with those 4 principles, we can explain why or what drives climate patterns on the planet. All right, now let's have you quiz yourself here to see what you know. All right, here's a map of the Earth on the Western Hemisphere, and we got three places labeled on the map. Well, 4, but three cities. We got Nome, Alaska, up at the top. We got Birmingham in the middle of the Northern Hemisphere, and we got Belém, Brazil, which is right there on the equator, and I got the equator labeled as well. All right. So, which of these, just answer based on your instincts, which of these cities gets the most hours of sunlight per year? So that's like from sun up to sundown, like calculate all those hours per year. Which of these cities do you predict gets the most sunlight per year? Okay, think about it. Pause if you need to, write down your answer, and then we'll come back to this in a few minutes. Okay, moving on. Hopefully you've written down your answer. I think you'll be surprised when we get to the answer in a few minutes. All right. Let's go back to 7th grade science, shall we? To understand what drives the climate patterns on the planet, we need to review some basics about the Earth and its movement around the sun. So here's a little cartoon to help us with this. Of course, this cartoon is not to scale. The Earth is not 3 or 4 times bigger than the sun, and we're not that close to the sun, fortunately, otherwise we would vaporize. So just keep that in mind. A couple other things to notice. Let me get my laser pointer going on here. You'll notice these arrows here that are connecting these different Earths. That's showing our rotation around the sun during this span of 1 year. And you'll also notice that Earth is tilted on its axis. It spins around on its axis. And that's this solid line here that you got going here. The dotted line represents, like if you had an axis running through the Earth that was perpendicular to the rotational plane around the sun. Like if you imagine this was a flat circle around the sun, that dotted line would be perpendicular to that. All that to show that Earth's axis is tilted off to the side, and that's one of the important things about that which causes seasonality. And here's why it's connected to seasonality. Because the Earth is tilted to one side, during part of the year, during this what we call in the Northern Hemisphere the summer months, the Northern Hemisphere is angled more towards the sun than the Southern Hemisphere. So here we are, and I'm taping this in August 2020. Right now we are just at the very beginning of starting to move into fall, okay? Meanwhile, in the Southern Hemisphere, they are just coming out of winter and just starting to move into spring, okay? So that's all because the Earth is tilted on its axis. If the Earth was not tilted on its axis, we would not have a change in seasons like that on the planet. And life for us would be very different. Human history would be very different. Okay, let's review, make sure I covered everything here. Earth spins on its axis once per day. I didn't state that, but I think you know that. Earth's axis is tilted, causing the seasons, and Earth circles the sun 1 revolution per year. Okay, so that's the starting point. We got a few more things to learn about this, though. Okay, same cartoon, but some couple points. All right. One of the key things here to understand is that all places on the planet get the same number of hours of sunlight all year long. But the equator, we all know, I think we all know, is much warmer than the poles, right? The cold zones on the planet are up near the poles, up at the top or up at the bottom, and it's the equator that's very warm. So why is that? Okay, to understand, we first have to get our heads wrapped around the fact that all places on the earth get the same amount of sunlight every day. Sorry, not every day, but all year long. So the way that it works is that because the equator is more angled towards the sun in a direct angle than the poles, the equator gets approximately 12 hours of sunlight each day, all year long. It varies a little bit the farther you are away from the equator. There's a little bit of wobble there, but not much. Okay. The poles, however, because of the way that they are angled away from the sun, they go through 6 months of essentially day and 6 months of night. There's an in-between zone when the sun actually sets and rises and you get a day and a night, but it doesn't last very long. You can see this in this illustration. So during the winter of the northern hemisphere, you see right here there's like a little circle drawn at the top. That's representing the Arctic Circle. And the Arctic Circle, above the Arctic Circle is all the land on the planet that goes completely dark for many, many weeks at a time. But then once the Earth, as it's rotating around the sun in the solar system, it gets to spring and it starts getting sort of some sun and some night. But by the time it's summertime in the northern hemisphere, the Arctic Circle is completely out of the Earth's shadow and is completely facing the sun all day, every day for the summer. Okay, all this to say, that the North Pole gets just as much sunlight as the equator during the span of a year. They just get it all at once during half of the year. And the same thing is true about the South Pole. It also gets the same number of hours of sunlight. Okay, so this is the beginning of answering the question why the poles are cold and the equator is warm. The equator gets warmed up every day of the year, whereas the poles have a long period of cooling down for 6 months, and it takes a long time to rebuild that heat. So that's one reason of several why the poles are cold and the equatorial zones are more warm. All right, there's more. Another reason why the equator is warm and the poles are cold have to do with the amount of energy that the sun beams onto the Earth's surface. So that's what I've got illustrated here with this cartoon. The yellow bands that are zipping across the white space there and striking Earth's surface, that is to represent rays of sunlight. And there's two scenarios here. In each scenario, it's the same amount of sunlight that is striking the Earth's surface. Okay. At the equator, because the equator is angled at a more direct angle to the sun, all of that sunlight is concentrated just in this short little area of that reddish pinkish dash that I drew on the Earth there. Okay, so all that sunlight is distributed in a small area. And because it's a small area, that sunlight is really dense. It's really intense. It's an intense amount of heat. Meanwhile, up at the poles, that same amount of sunlight would be distributed over a lot of land surface that would stretch from here all the way up to there. So it's the same amount of sunlight striking the Earth, but it's spread out over a larger area. Okay, so one way that I'm thinking about it, because my daughter just made a cake recently, it's kind of like you get X amount of icing and you can spread it out over a small area of cake and have a lot of icing with one bite, or you can spread that icing out over a larger area of cake and not get quite as much. That's what's happening to help cause the poles to be a lot colder than the equatorial zones. Because all that sunlight is delivering heat as well as light, and with that sunlight distributed over such a large surface area, it allows, it just doesn't carry that much energy relative to the equator, and so the poles tend to be colder. Okay, so for these reasons, the Earth has different zones, different temperature zones on it. And so we divide up the Earth into the zones that you see here. Yep, my coffee's still warm, yum. We got the polar zones at the top. It's really cold, and that's above 66.5 degrees north latitude or south latitude. And then we've got the equatorial region, or the tropical zones, that range between 23.5 degrees south and 23.5 degrees north. And this is the zone that we call the tropics. Everything in between we call the temperate zone. Now, climate doesn't change sharply at these boundary zones. It's more of a gradient, but these are just helpful constructs. The reason these lines are on the map have to do with the sun's angle and how the sun behaves relative to the Earth's surface. I already explained how the polar zones go through a phase of time when you get 6 months of darkness and 6 months of light. Well, the boundary here for the tropics has to do with as the Earth spins or goes around the sun during the course of the year. This is the farthest north point where the sun will be directly overhead at least one day during the year. This is the farthest south point when the sun will be directly overhead one day during the year. This is just kind of an FYI. You don't need to know about like what causes those boundaries, but I thought you might be curious why they're there. Okay, so the main message here, the important message, is that we divide the Earth into these temperature zones: the polar zone, the tropical zone, and the temperate zone in between. All right, let me quiz you here. Do you know the answer to this yet? And this is the same question as before. Which of these three, if any, gets more sunlight than the others? And the correct answer here is D, none of the above. They all get the same numbers of hours of sunlight. Blim gets more like 12 hours of sunlight every day. Nome goes from like 0 sunlight a day to full-on 24 hours of sunlight a day, depending on the season and with the in-between phases as well. Okay. All right, so those are the reasons why we've got the temperature zones and all that. Now let's take a look at Alabama. How does Alabama fit in all this? Now, why the focus on Alabama? Because we're trying to solve that mystery. Why does Alabama have so many species? Okay, so what we're looking at here is a temperature map, although I'm realizing that this temperature map is outdated now because of climate change, but that's okay, we're going to use it anyway. This is showing, the map on the right is showing the average temperature for different regions in the state during the course of the year, and this is in degrees Fahrenheit. And notice that up here in the Tennessee Valley area, the temperature ranges from 60 to 58 degrees as your average temperature during the course of the year. Whereas down here at the Gulf Coast, temperatures range from 68 to 70 degrees on average over the course of the year. So this is like taking the average temperature for a day and then averaging all the averages of all the days of the year, and that's the number that you get. And the map is broken into these gradients of 2 degrees, 68 to 66, 66, 64, that sort of thing. Okay. The important point I want to make here is that we have a pretty substantial temperature gradient in the state that's about 10 degrees from 58 to 60 here in the north to 68 to 70 in the south. That means that we've got some plants and animals that are more tropical in their behavior and their growth down here in the southern part of the state. And we've got species growing in the northern part of the state that are much more like the colder climate species that we find farther north. If Alabama was a squat state like Tennessee, we wouldn't have so much climate variation. But instead, we're kind of long and drawn out north to south, and that helps us have a lot of climate variation. A couple other things. Southern Alabama is warmer than the north because it's closer to the equator, so it gets more intense sunlight than you get farther north, and it's enough to make a difference. And of course, yeah, and so that's the main reason there. Also, the southern Alabama is closer to the Gulf of Mexico, which warms up during the summers and retains a lot of that heat during the winter. And the Gulf winds up keeping lower Alabama much warmer than it would be otherwise. So it's kind of like lower Alabama is sitting in the summer. It's like it's sitting next to a little heater down there, the Gulf of Mexico. Okay, so that helps explain why we have the temperature variation that we have in the state. Okay, this might be a good place to pause for you because we've covered a lot of information. Check over your notes and that sort of thing because we're about to get into this, the most complex part of this class. So go ahead and do that if you need to. I'll have a sip of coffee. Yep, still warm. All right. What we're looking at here is a map of the planet, and with these crazy three-dimensional arrows representing general wind patterns on the planet. And it's not just wind, it's also the movement of moisture. That's what the red shading that you see on these arrows is representing, which is moisture and rainfall. I'm going to walk you through understanding how this works. There's a lot of text on this slide that will help you with this when you just want to pause and study the slide. Okay. All of this, that I will explain, leads up to explaining why the Earth has 3 zones of high rainfall on the planet, one at the tropics and one farther north and one farther south, and why the planet has 2 dry temperate zones on the planet, one at about 30 degrees north and one at about 30 degrees south. So it's very dry zones, and why the planet has 2 polar zones that are also quite dry, which seems counterintuitive because there's a lot of ice up there, but I'll explain. Okay. All right, so here's how this works. Let's imagine that we wake up tomorrow morning and we're in Belém, Brazil, which is right on the equator. The sun comes up around 6 in the morning, and it's really cool. It's a wonderfully diverse city. We go to the market. It's really cool. There's fun stuff, lots of tropical fruits and fishes out of the Amazon, and we're trying to understand our Portuguese and that sort of thing. And by about 7 in the morning, you're starting to notice, dang, it's hot. It's only 7 in the morning. Well, that's because the equator is angled closer to the sun with a more direct angle to the sun. So the sunlight that is striking the equator and the whole equatorial zone tends to be much more intense, like we talked about before. So things heat up very early in the morning, very quickly in the morning in the tropics. Now, when water is warmed up, what does it like to do? It likes to evaporate. And so as the sun rises and starts baking the tropics, a lot of water is evaporating out of the forests, out of the lakes, the rivers, everywhere, out of the soils, all that sort of thing. And so all that water warms up and it evaporates and goes into the atmosphere as water vapor. So that's gaseous water. Now, what does warm air like to do compared to cold air? Hopefully you answered it likes to rise, okay, because that's what it likes to do. That's one of our physical properties. So that warm air starts to rise off the landscape. Now, what happens to warm air as it rises? Do you remember? Hopefully you remembered that warm air likes to cool as it rises. So as that warm air rises, it starts to cool, okay? Now, that warm air is carrying all that moisture that evaporated off the landscape. What happens to air as it cools? Is it able to hold on to that moisture? No, it's not, because cold air does not hold moisture as well as warm air. And so what is happening here is that the Earth's surface is getting heated up by the sun. That's causing evaporation of water. And it's also causing the Earth's surface to heat up and then radiate that heat into the lower atmosphere, the air that's all around us near the surface. That warm air near the surface, now with all that water vapor in it, wants to rise, and it starts rising. And as it rises, it gradually cools. And as it cools, the water vapor starts turning into little droplets. Okay, those little droplets are what we see in clouds. We're seeing little droplets of water gathered together to form clouds. Okay, so what happens is that warm air rises. Once it gets cool enough, you get cloud formation. But guess what? More warm air is coming and it's loaded with more moisture. And so you wind up getting the clouds growing and growing and growing. And, and you wind up having those clouds sort of building upwards to even higher elevations in the atmosphere. And as at some point, rain starts to fall because those little droplets, those cloud droplets, start bumping into one another. They stick together, they form bigger droplets bump into each other and form even larger droplets, and eventually it becomes a raindrop. And that's why you wind up getting in around mid-morning and midday in the tropics lots of rain on a typical day. Okay. So what's essentially happening here, I should have been referring to these arrows over here. What we're seeing is warm air rising up off the surface with water vapor. That water vapor then turns into rain and comes back down as rain. And so the equatorial zone around the planet tends to get lots of rain all year long. Now, that air that was traveling upwards, it doesn't just stop once the clouds form. It can't, because more warm air is coming right up behind it and pushing it to higher elevations. But it can't keep going up forever. If it did keep going up forever, the Earth would lose all of its atmosphere, and that would really suck because we'd die. Everything else would die too. So what happens instead is that gravity winds up pulling that air back down. And so what happens is up at the high elevations, the gravitational pull on the air starts pulling it sideways. Some of that air flows northward through the northern tropics. Some of it flows southward through the southern tropics. The air doesn't drop down into the tropics because all through the tropics you're having warm air rising. This is a very simplified model of what's happening. There's a loop here, but it's a very messy loop. You got lots of more air joining it, rising up throughout the tropics, okay, all the way up through Mexico and so forth. Now, this air that's in the upper atmosphere that's now traveling northward, it's now very dry air. It's cool because it's at higher altitude and it's dry. And it doesn't keep going up. It doesn't just keep going northward. It winds up being pulled back to Earth's surface for two reasons. Number one, gravity is pulling it down. And once it gets far enough north, it doesn't have strong thermals that are bringing warm air up from the surface as much anymore. So it's able to fall down to the Earth's surface. The other thing that happens is that it runs into air coming down from the north. We'll explain what this loop is about in just a few minutes. All this to say that this air that started off warm and full of moisture is now at a high altitude and it's traveling northward and it's dry. It's cold and it's dry and it winds up falling on the Earth's surface. And it winds up falling on the Earth's surface around 33 degrees north. Okay? So as that air descends, something changes about it. Maybe you remember this from before. That air descends and it warms up. The reason it warms up is that the lower it gets in the atmosphere, the more squeezed together those air molecules are because of the surrounding air that gravity has pulled down close to the Earth's surface and squeezed all those molecules together and crowded the atmosphere with air molecules down close to the surface. So as our descending air, our falling air gets closer to the surface, it gets squeezed together in a smaller and smaller space. The air molecules bump into each other more and more and more, and that's essentially warming it up. Okay, because remember, temperature is a measure of that molecular motion. So by the time this air winds up hitting the Earth's surface, it's warmed up considerably and it's also really dry. What sort of ecosystems would you expect to find at a place where you've got lots of warm, dry air? We'll come back to that in a few minutes, okay? Now, I should say that everything I'm explaining up here in the northern hemisphere is happening in the southern hemisphere, but I am certainly not going to go through all those arrows. So we're going to just wrap up here with the northern hemisphere and then move on, okay? This air that drops down at around 30 degrees north, it can't just sit there because more air is coming up behind it. So some of it flows across the Earth's surface back towards the equator. As it does that, it's absorbing heat from the Earth's surface, heat that the Earth got warmed up by solar radiation, the sunshine warming up the Earth's surface, and then the Earth's surface radiates that heat into the atmosphere and warms up this air as it moves along the surface. And that air starts picking up moisture as water vapor, as water evaporates and loads that atmosphere with, or loads those winds with water vapor. And then the cycle just continues. You get that warm, moist air rising up again and more rainfall, okay? In the temperate zone, a similar thing is happening. Some of that air is going to travel northwards along the Earth's surface. It's going to warm up even more as it does. It had already warmed because it came down from the higher altitude, but it's going to warm up more as it travels across the surface. And it's also going to pick up moisture. And when it gets to around 60 degrees north, it winds up colliding with air that's coming down from the pole in this loop that's up here. And that forces all that air from the pole as well as from farther south to rise. And of course, as that air rises, it cools. And when it cools, the moisture comes out of the water vapor form and turns into droplets that fall down as rain. That's why we've got a belt of rain at about 60 degrees north. This is why it's very rainy in Seattle and Vancouver and Alaska, parts of especially southern Alaska and much of Canada. Okay? That air rises up. Now it's cold and dry again. Some of it travels south to rejoin this loop and kind of goes around and around. Some of it travels north, winds up hitting other air that had been traveling north, that pushes it back down, travels across the surface, and you wind up having this loop, okay? So we've now gone through these three, or there's six really, but these, within any hemisphere, there's three of these loops. There's the tropical loop, the temperate loop, and the polar loop. And that helps explain why we've got these different zones of rainfall on the planet. We got one at the equator and one at 60 degrees north and 60 degrees south. And it explains the dry zones we have on the planet. There's one at each of the poles, okay, because there's no moisture very little moisture falls up here. And we also have the dry zones at 30 degrees north and 30 degrees south, okay? All right, that was a lot. I know you may need to replay that a couple times to get all that, and certainly email me or ask me during class if you want some further explanation. All right, my coffee's still warm, which is good. Okay, so this is a good quiz for you to see if you got all that. So here's your question. Based on what we just covered, what's the predicted climate in Alabama? Taking a look at this map, is it warm and wet, warm and dry, cool, wet, cool, dry, hot, wet, hot, dry? What would you predict? All right, so if you reviewed your notes and thought through this based on what we've just talked about, you should predict that, that the climate in Alabama should be warm and dry. It's warm, not hot. The equatorial zone would be hot. The poles would be cold. So warm would be the appropriate descriptor. And we'd expect it to be dry because of this dry air descending from up above and causing a very dry climate. I don't know about you guys, but Alabama is definitely warm, a little bit on the hot side, I would say. And it is most certainly not dry, not during a typical year anyway. So something's going on. Okay, what is going on is that this is a generalized model about the climate on the planet. There are going to be local variation. There's going to be local variation, and we're going to talk about what causes Alabama's local variation because it's really important. Okay. All right, so what's going on to cause all this? Okay, to get at this, to understand the significance of those climate patterns, those generalized climate patterns, and also what's going on in Alabama, I need to introduce another term, and that's biome. A biome is a large region of land characterized by having a similar climate, similar ecosystems, and similar plant and animal communities. I had a nice graphical cartoon on the previous class that showed you the differences between individuals, populations, communities, ecosystems, biomes, and biosphere. You might want to refer back to that when you are developing your study guide to understand biomes. I got two pictures of here, one of a desert biome and one of a rainforest biome. Within this desert biome, you've got several ecosystems. You've got these exposed, bare sections of rock that are really dry and harsh. You've got your little valley bottoms down here where moisture collects when it does rain. You can see that dark green throughout there. That would be a different variation of the ecosystem. And then in the far distance, you can see some taller mountains. Things will be slightly, well, actually a lot cooler at the higher elevations up there. There's probably even some forest in some of those valleys. Okay, so but all of this is very similar to, between these different ecosystems is very similar, and so we lump it together and call it the desert biome. And there's tropical desert biomes and there's temperate desert biomes on the planet. Your textbook walks you through that. Okay. Anyway, within the rainforest biome, you would also have different ecosystems. There'd be your valley ecosystem, your hill slope ecosystems, and your higher elevation ecosystems. Okay, so that's what a biome is. Now, biomes are not random across the planet. They have a lot to do with the climate, and we see that here with this illustration. The tropical rainforest biome tends to be found, in the tropics, closer to the equator. And then as you travel farther north in the temperate zone, you get into temperate forest. And then if you get far enough north, you start to get to a forest where you don't have broadleaf trees anymore. It's mostly conifers, like spruces and firs and larches and things like that. That's what you would have up in Minnesota and farther north. That's what you have in Seattle and Washington State and so forth, okay? That type of forest is called taiga, T-A-I-G-A, taiga, okay? If you keep going north, you're going to get past the tree line into an ecosystem called the tundra. The tundra doesn't have trees, it just has short vegetation that's covered with ice and snow for much of the year. And then you go even farther north and you're going to get to the polar ice zones. Okay, so all this to illustrate that you've got different biomes on the planet arranged around a gradient from north to south. All right, what kind of biomes do we have in Alabama? Well, our primary biome is what's called the temperate deciduous forest. And so temperate refers to the temperate zone. We're not the polar zone. We're not the tropics. We're kind of in between, the Goldilocks zone, if you will. And deciduous deciduous trees are the trees that drop their leaves for much of the year. And so the typical Alabama forest is a temperate deciduous forest. But we also have some secondary biomes. We have sections of the state that are evergreen. They're dominated by pines. And so we do have temperate evergreen forest. And there's even many portions of the state that were originally grassland and prairie, and that would be considered temperate prairie or temperate grassland biomes. So Alabama has 3 terrestrial biomes. Terrestrial, what does terrestrial mean? That means land, okay? Terrestrial versus aquatic, okay? All right, I don't want to throw lingo out there. Sometimes I slip up and do that. Okay, so if the, that pattern, let me just toggle back. If this pattern here on this map were all there was to understanding where biomes are on the planet, ecology would be a lot simpler. But instead, there's a lot of variation. And there's several different reasons that there's variation, and we'll get to those. But that variation leads to a map of biomes that's a lot messier than what you might expect if there was going to be clean patterns here. So let's first of all look at the patterns that are here, and then we'll look at where there's a lot of variation. So check out this deep indigo color here. That's that taiga forest, the spruce and the fir forest, full of conifer trees, pine trees, pointy pine trees, if you want to think about it like that. Okay, that band, there is a distinct band of that biome across the planet. Here it is across North America, and then it picks up again um, in Northern Europe and across Eurasia, all the way across. Okay. Another band that you can see is our tropical rainforests in deep green here, ranging from here in the Amazon basin across here, Africa, and then parts of the South Pacific. Okay. You also have, for example, dry zones on the planet. So at about, remember how I said earlier that at 30, let me go back to the map. Boom, here. Okay, at 30 degrees north and 30 degrees south, dry, warm air is descending onto the Earth's surface. Well, guess what? Look at 30 degrees south, which is about here. We've got dry, very dry climate here, a little bit further than south than 30 degrees, but that's okay. It still proves the point. And we got dry desert conditions in the very southern part of Africa, and of course, most of Australia is desert. In the northern hemisphere, we've got the dry deserts of the southwestern US and northern Mexico. We've got the Sahara Desert, big old desert there, and we got the Middle Eastern deserts here as well. So yes, we do see echoes of those climate patterns determining where the biomes are on the planet. But still, there's a lot of variation. Check out the Southeast. We would expect the Southeast to also be desert, but it's not. Instead, it's shaded in the brown, and then parts of Florida in that light green. Well, let's translate that. The brown is the temperate deciduous forest that I've told you about. And the Gulf Coast and parts of the Southeast Atlantic coast in Florida is warm, moist evergreen forest. Okay? So those are not the biomes that you would expect based on those big climate models. And the reason is that there's a lot of variation. So that leads to the question, which is, why does Alabama not look like this desert picture that we have on the right? This is a picture from basically the same latitude as Alabama, but over in Arizona. That's the Sonoran Desert. You can always recognize the Sonoran Desert because it's got those beautiful saguaro cactuses that you see, those tall cactuses that look like they have their hands up. So why isn't Alabama a desert? The answer has to do with the fact that you've got 4 different things causing regional climate variation on the planet: currents, monsoons, rain shadows, and elevational temperature gradients. And the 2 that are highlighted in orange are really important in Alabama, and we're going to talk about all these. Okay, let's talk about ocean currents first. Just as I described how there are air currents in our atmosphere, those big loops, those 3 loops that we have in each hemisphere, just as there's warm air rising and cold air sinking happening, you've got, for the same reason, you've got currents in the oceans where you've got warm waters that rise to the surface and cold waters that sink to the depths of the oceans. And that winds up creating, that is one of the reasons that winds up creating these major currents that move around through the world's oceans. The warm bands that you see here represent the sort of the general trends of water currents as they're moving around on the Earth's surface. The red bands here are the warm waters, and the blue bands are the cold waters. So let's check out what's happening in the Atlantic. You've got a current that crosses the southern Atlantic. It enters the tropical zone here. It gets superheated in the tropics. It goes up into the Gulf of Mexico and then shoots out through the Florida Straits here between Florida and Cuba. And because it got squeezed through there, it shoots out here really fast. That's the Gulf Stream. And this warm water is carried all the way across the Atlantic to bathe northern Europe in warm water, oceanic water, much, much warmer than it would be otherwise. However, the atmosphere is cooler up there, and that warm surface water winds up cooling, and when it cools, it winds up sinking. And so you have another current, a countercurrent, that drops out here at a much greater depths in the ocean and travels all the way back down here to the southern atmosphere, to the southern hemisphere. Okay, all this to say that we've got currents that move waters around, and those waters carry heat. If it wasn't for this warm water of the Gulf Stream, northwestern Europe would be a very different culture, very different economies and ways of living would be up there because it would be much, much colder, for example. Okay. All right. So this causes some of this biome variation. That's why that previous map all the way here isn't quite as clean as you would expect based on that map. Okay. All right. Now, so currents are one thing that cause regional variation. Let's look at that, how it affects Alabama. All right. So I showed you before, here it is again. You've got this current here that crosses the Atlantic, collides in the Caribbean, winds up getting a lot of that water funneled into the Caribbean Ocean here, and then that shoots into the Gulf of Mexico and then comes out through the Florida Straits there. We're going to look at that at more resolution here. Okay, that's what's happening here is that same current comes into the Gulf and then leaves the Gulf. You can ignore these over here. These are little eddies that happen, little spin-off eddies from the current. We're not going to talk about those today. This main current, though, that comes up into the Gulf, this is called the loop current because it forms a loop. Very imaginative, huh? And the loop current winds up bringing warm water to our doorstep of the southeast all year long. All right. Now, warm water loves to evaporate, and in the Gulf of Mexico, we're farther south enough that the sun heats up that water even more, and so you wind up getting a lot of water vapor evaporating off the Earth's surface. Well, guess what happens? Those winds that we saw back on this map, where are we? Here we go. These winds, these north traveling winds across the surface, they wind up taking that water vapor and taking it into the interior of the continent. Okay, so what that means is that because of the loop current, it's bringing a lot of heat as well as moisture to the southeast all year long. And that's what is bathing the southeast in so much water. That's why the southeast is wet. And why the southeast is moist. It's a very wet region all year long. If the Gulf of Mexico wasn't there, if we were to close this off and fill it in with concrete or pump it dry, we would wind up having a much drier climate here in the southeast in Alabama and adjacent states, more like what we have out in the western U.S., like in Arizona and New Mexico. Okay, this is why the loop current is in the Gulf of Mexico is why Alabama is not a desert. Okay, this is showing annual average rainfall or precipitation. So this includes snowfall in the lower 48 states, and you see that the more cooler colors represent higher levels of rainfall. And there's two places in the U.S. that get lots of precipitation. There's the Pacific Northwest, of course, and then there's the southeast. And the southeast is the biggest zone of high rainfall in the lower 48 states, U.S. states. Without the Gulf of Mexico, we would look something more like this. Okay, moving on here. All right, a second reason that causes regional variation to climate patterns have to do with monsoons. You've probably heard of monsoons before, and maybe you know that they are very rainy seasons that you have in places like India and Southeast Asia. That is exactly true. You're right about that. Monsoons only occur, though, in places where you have land that is north of a warm ocean. In the case of Southeast Asia and India, let's go back to the global map here. Here we've got the Indian Ocean on either side of the Indian subcontinent, and it's in the tropics, so these are very warm oceanic waters. You also have lots of warm oceanic waters here in the South China Sea and all through the waters here next to Indonesia and so forth. So all these lands up here are to the north of warm tropical waters. And what that means is that you get the monsoon. and I haven't explained why, but I will in just a moment. Okay, here's how a monsoon works. Okay, um, during the summer in the northern hemisphere, the land heats up a lot faster than the ocean. Remember, that was one of our physical properties, that land and air temperatures heat up a lot faster than water. So during the summer in the northern hemisphere, the land heats up a lot faster than the ocean. And so that warm air that sits over the land winds up absorbing that heat as it's radiated off of the land, and then that warmed air winds up rising into the atmosphere, just like we talked about. Well, if fortunately that air is replaced by air coming in from adjacent areas, otherwise we would all suffocate, right? And for Southeast Asia and India, and also the southeastern U.S., you wind up getting air pulled off of the ocean or the water body that's to the south. For us, it's the Gulf of Mexico. For India, it's the Indian Ocean. Okay, and that air comes in. It's warm air. Don't think of it as cold, even though these arrows are blue. It's warm air, but it's not as warm as what's over here on the inland. Okay, and so you've got warm air loaded up with moisture, comes onto the land, gets superheated because it's so hot on the land surface relative to the temperature of the ocean. It gets superheated, that air rises up, and you get lots of rain. Rain and rain and then more rain. The tropical monsoons of India and Southeast Asia, there will be, and even parts of Africa, it will rain day after day after day after day, and sometimes not stop for days and days and days and days. I can say firsthand because Africa gets a monsoon as well, and there was just like weeks and weeks where we never saw the sun. Okay, so this is what happens during the summer for a monsoon. During the winter, the whole thing reverses. Um, During the winter, the land cools down rapidly because land and air cool down much more rapidly than does the ocean. The ocean, meanwhile, is like finally caught up, and it's like finally got all this heat, and it's like, all right, I'm ready to party. Let's do this. And the land and the air are like, dude, we're cooled down now. And so what winds up, because there's that temperature differential, you wind up having a lot of air. Um, That's my mom. She can wait. Um, you wind up having a lot of air evaporating off of the, I'm sorry, a lot of water evaporating off of the ocean here and rising up. And so your rains are now offshore instead of on the land. And so this is when you get the dry season in India and Southeast Asia. So if you ever get a chance to travel in those countries or those regions of the world, pay attention to the weather. You're not going to want to go during the monsoon rains because you're going to want better weather than that, I promise you. Okay, so toggling back one slide, Alabama gets a summer monsoon. That's why we get a lot of rain, especially closer to the coast during the summer months. But during the winter, we get a different cycle. I thought the slide was next, but it's not. Where is that slide? Here's that slide. You're going to have to jump ahead when you look at the PowerPoint. This is what happens in Alabama in the summer. We wind up getting cold fronts coming in, so chunks of cold air that are coming down from the high Arctic, and those create these cold fronts that wind up lowering temperatures, and we get cold, dry air for a while, and then we get a warm front that pushes back. That's basically the Gulf of Mexico pushing back and reclaiming territory and filling the southeast with warm, moist air for a while. And then the cold fronts come through, and it rains and it storms, and then we get dry, cold air for a while, and then that peters out, and the Gulf pushes back, and it goes back and forth, back and forth, back and forth. That happens all year long, but it's really subtle in summer, and it's much more pronounced in the winter. Okay, so all that to say that Alabama has a summer monsoon that helps to explain why it gets so much moisture during the year. Okay, so we're starting to wrap things up here, which is good. We got a couple more points to cover, but we're getting there. Let's ask the question about the role of climate in Alabama's biodiversity. So how important is it for explaining why Alabama has so many species? And the answer is that it's important, but not super important. And here's why. Louisiana, Mississippi, Alabama, Georgia, South Carolina, they're at all about the same latitude, so they get the same amount of intensity of sunlight all year long. They are very similar in terms of their their location relative to the Gulf of Mexico and so forth. But those numbers that you see there on the map, those indicate state rankings for total biodiversity. So Alabama's ranked number 5 among U.S. states, Georgia number 6, but Mississippi is 17, South Carolina 14, Louisiana 18. If climate was the main driver of biodiversity patterns and why Alabama has so many species, we would expect those numbers to be very similar across the states, but clearly they're not. Something else is influencing Alabama's landscape to cause it to have so many species. And I think, as you already know, because I told you up front at the beginning of this, it has to do with geology. Okay, we'll come back to that in a different class. All right, a couple more things to wrap up. I was going through the 4 different ways that you get regional climate patterns that vary from the overall general climate model for the planet. A third one is rain shadows. This is when a mountain chain, or even tall hills, but usually it's mountain chains, wind up forcing air currents or winds to rise in elevation. And as they rise in elevation, that causes the air to cool and the moisture to drop out as rainfall. And then that air keeps traveling over the mountain, and after it's gone through the mountains, it warms because it drops in elevation again, and it's drier because it left all its moisture on this side of the mountains. This is why if you were to go to a place like Portland or Seattle and travel from the coast into the interior of the state, you would go from the shoreline of the Pacific Ocean, you go through a very moist ecosystems up through the mountains, and then on the other side and into desert conditions in western Washington and Oregon. These are called rain shadows. Okay, we get a little tiny rain shadow in the Appalachians, but it's very small and kind of localized. And then a fourth and final reason for regional variation has to do again with mountains. You get altitudinal variation. Remember how I explained early on, look over here to the way on the left, how you have colder air at higher altitudes? Well, when you have mountains that are tall enough, you'll get cooler air temperatures, and that winds up supporting different biomes. So just as when we go from, if you look at this cartoon on the right, just as we go from the equator here through tropical forest all the way up to polar ice and go through those biomes, you can see a very similar transition of biomes from the lowlands in the tropics all the way to the high glaciers that you have in the tropics. You can see these in places like the Andes in South America. You can be in tropical forest in the morning, and then if you'd have to drive all day, but if you drive long enough, like about 4 or 5 hours up some winding roads and stuff, you'll get up into the tundra zone, into the ice zone, and go from tropical forest to what feel like Arctic conditions within the span of just one day. That's why the tropics are so cool and so interesting, I should say better, for all the biology that's there, because you get all those biomes in such a short distance. You don't have to travel as far. Okay, folks, as promised, that's a wrap. We're done. That's your introduction to global climate patterns. And we're going to next take a look at other factors shaping biodiversity, especially geology. And then later on in the course, we're going to circle back to these global climate models to help understand climate change and how that's affecting our lives and what's happening on the planet. All right. See you guys in class, or hear you guys in class, either way.